Hi, and welcome to part 3 of our review of complex variables. This review is specifically intended for students in the ECE 3337 Signals and Systems Analysis class. Okay, this is the third part of a 3-part lecture series. In the first part, we looked at some basics. Okay, complex numbers, how to represent them, how to look at them, how to consider their angles and things like that. We also introduced Euler's formula. And then in part 2, we looked at complex functions. That's a way of transforming variables. And complex functions is something we need in order to describe signals, systems, things like that. Now in this third part, we will talk a little bit about how to do some basic kinds of calculus with complex variables. Again, this subject is way bigger than what I'm describing. Okay, I'm just going to focus on the things that we need just to get by in this class. Okay, so we're going to look at the notion of limit of a complex function. We'll look at how to differentiate and integrate complex functions. Again, I've been repeating this over and over again, but in case you got to this third part without having looked at the other parts, I wanted to make sure to remind you that complex variables is ordinarily a full semester course, or probably multiple semesters long, depending on how deep you want to get into the subject. So these lectures are not intended to be comprehensive, right? They cannot pretend to be so. They are not a substitute for a full course, especially something that would be offered in a mathematics department. My goal here is to simply remind you of things that hopefully you've already encountered. Like I said, these topics that I've picked are specifically limited in terms of scope to what's needed to get by in ECE 3337. I'm not going to be doing theorems and proofs or even approaching that level of rigor. I'm just going to focus on intuition and practical realities. Okay, so join me. Let's go. By the way, again, at the risk of repeating myself, try and get one of these textbooks. Okay, they're easy to get a hold of, they're cheap, and it's nice to have them around. Okay, and of course, use them. Don't just keep them. So now in part 2, we looked at complex functions. Not every complex function, but just a subset of them that are well behaved, and the ones that are needed just for this course. Okay, like I said, it doesn't mean that every complex function is well behaved, right? So the subset of functions that we talked about, okay, they behave largely like their real cousins, and I tried to pick on a few cases where they can be a little different. For example, logarithms, right? A logarithm is a multi-valued function in complex algebra, whereas, or complex mathematics, whereas, in the world of real variables, it's not quite so. We talked about the notion of a complex zero, and we also talked about the notion of complex infinity, right? We'll touch base on them again today in this third part, just for good measure. Again, please study a math textbook or take a math course to get a deeper understanding of this subject. And we are only taking kind of a relatively shallow and practical look at these concepts with just ECE 3337 students' needs in mind. So as a recap, a complex function, okay, is a mapping that assigns a real number, a complex number z, okay, and you can think of that as an input, and the function, okay, takes this input and then spits out an output. Okay, suppose we refer to that as w. Okay, w is f of z. Now z is x plus jy, or in polar coordinates it's a radius and a magnitude and an angle theta, right? And we can write this function as the sum of a real part, u of xy, or u of r comma theta, okay, plus j times v of xy. Okay, and also we talked about the fact that, you know, u of r comma theta plus j of v of r comma theta, okay, these u's and v's are different, okay, because they're functions of different variables, even though they're kind of related, but they're different. So if you ever want to use these at the same time, you know, try and stick a superscript or subscript or something to distinguish them. For our purposes, okay, we're going to use one or the other, so there'll be not much confusion from that side. Okay, let's try and do some calculus, right, with complex variables. Now, in doing calculus with complex variables, okay, we need to always keep in mind that we are operating in the complex plane, right? And the complex plane is a two-dimensional thing, right? You got the x dimension and the y dimension, and the complex number can live anywhere in this plane, and not just on one line, one of these lines or anything like that, right? And this fact that it's two-dimensional is an important source. For our purposes, the main source of differences between calculus with real variables and calculus with complex variables. Okay, that's because if you have a point, yeah, and you need to look at its vicinity, how you approach that point varies, right? On just a one-dimensional plane, there's only one way to approach it, or maybe two. But here, there's an infinite number of ways to approach a point in the complex plane. We'll get to that in just a little bit. Okay, and some of these differences will also become front and center when we are dealing with some extreme situations. You know, something is zero, or something is infinity, or a denominator approaches a zero, or some singularities and things like that, right? Now, when we're not dealing with such situations, our life will be very much similar to what it was with real variable calculus. So one of the important notions in calculus is the idea of a limit, right? So the idea is the following, right? As let's go back to our familiar sort of real variable example, right? So suppose I had a function f, and it was given by, say, sine of x divided by x. Okay? Now I can ask the question, what happens to f of x as x approaches 0? Right? So the limit as x goes to 0 of f of x is what? Okay? Now I do know, and I can sort of see right away, that x is in the denominator. Okay? So this function is not actually defined at x equals 0. Right? So we are talking about, approaching 0, okay, but not getting, sitting at 0. Okay? So we are talking about infinitesimal neighborhoods of 0. Okay? These neighborhoods can become tiny, 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 and tiny. Okay? And as that happens, it turns out that sine of x, its value is not that different from x. It's about the same, right? So in tiny neighborhoods, when x is very tiny, then sine of x is about the same as x. So their ratio, okay, is about x. So this limit turns out to be 1. In much the same way, okay, in the world of complex variables, okay, when we ask about the limit, we can ask about a limit of a function even though the function itself is not defined at that point. Okay? So we say that a real valued function, u of xy, okay, has the limit, okay, u naught. Okay, so suppose we ask, what is the limit of this as xy approaches x0, y0, okay? And if that happens to be u naught, okay, provided that the value of u, okay, gets arbitrarily close to u naught, as xy gets arbitrarily close to x naught, y naught. Okay, so let's see how that works, right? So suppose you have a point in the plane, okay? Suppose I call that z is xy, okay? And then I have another point, say z naught, which is x naught, y naught, okay? We're talking about this guy sort of approaching this, and as that happens, the value of u approaches u naught, okay? So the one twist that comes up in the complex plane is how you go from here to here, right? And the real axis, there weren't too many ways, right? If you wanted to get to 0 and you were on the x-axis, you could either go like this or like that, right? There weren't only two ways. But here, there are a lot of different ways. What if you go like that? What if you go like that? What if you go like that? And so on, right? So depending on the path that you take, okay, one question is whether this, u approaches the same number u naught. Okay, now if that happens, that regardless of what path you take, u approaches u naught, then we say that this limit exists. Okay, if that is not true, even if you can find one exception, okay, which means that suppose I can find two different paths for which I get two different answers, okay, then I can say that the limit does not exist. Okay, in other words, the value of u naught must not depend on the path that you take in going from, okay, x, y to x naught, y naught. Okay, does that sound good? Okay, so, okay, now there's another aspect to this. So if you want to prove that a certain limit does not exist, then you just have to find one counterexample, right? So showing that a limit does not exist is actually surprisingly simple, okay? It's a much lazier process than showing that a limit exists, right? Let's look at an example. So consider the following functions, okay? So u of xy is xy divided by x squared plus y squared. Okay, so one path that we can take, let's call it path number 1, is to suppose we approach along the x-axis, right? So along the x-axis, we know that y equals 0. Okay, so basically, you take a path like that. So this is your 0. Okay. Now, by the way, I forgot to mention, we're interested in the limit of u of xy as xy, okay, approaches 0, 0. So this is the point that we're interested in, and we want to approach that like this. Okay, so let's take y equal to 0 into this function, right? So you get u of xy is simply x times 0 divided by x squared plus 0, which is just 0. So no matter what you do around here, the answer is just 0. Okay. Now let's consider path number 2. Okay. Now another path that we can take is the path along the 45-degree line. Okay. So if we consider the path along the 45-degree line, along this line we know that x equals y. So let's see what happens when x equals y, right? So in that case, u of xy, okay, is x times x divided by x squared plus x squared, right? So this is basically half, right? X squared divided by 2x squared is half. Now, the problem is that this number and this number are different, okay? So the limit does not exist. Okay, let's get to the next slide. So if we are given a complex function, say f of z, okay, and we are asked to, and f of z is given by, say, u of xy plus j v of xy, right? And suppose that we're asked for the limit as, z goes to z naught, where z is xy and z naught is x naught y naught, right? Okay. And suppose this limit is given by u naught plus j v naught. Okay, and let's call that collectively the complex number w naught, right? So we can find the limit of a complex function by finding the limits of the two parts of it, the real part and the imaginary part, right? So in this case, okay, the limit as z goes to z naught, okay, of u of xy is u naught, and limit as z goes to z naught of v of xy is v naught, right? Now, just like in the example of sine x over x, okay, this approach works even if f of z is undefined at this point, z naught, okay, or x naught, y naught. So let's look at some of the properties of limits, and these properties are helpful to us because, we can take advantage of them to make our job easier, right? So suppose you have two functions, f of z, and you have another function, g of z, and suppose their limits exist, right? So suppose the limit as z goes to z naught of f of z is, say, a, and suppose the limit as z goes to z naught of g of z is b, right? So these two limits exist, right? And we know what they are, right? So in other words, you can get to a regardless of how you get from z to z naught, and you can get to b regardless of how you get from z to z naught, right, for g of z. In that case, suppose I look at the sum of g and, f and g, and ask what the limit is, right? Then this is simply given by a plus b. And conversely, okay, or as an aside, if this happened to be a minus sign, then this will also be a minus sign. So the if I'm given a sum of functions or a difference of functions, okay, I can essentially do something like this. I can say this is equal to z goes to z naught of this plus limit as z goes to z naught of g of z, okay, and that's equal to a plus b, and of course a plus or minus b, right? So this is also true for, okay, f of z times g of z, and f of z divided by g of z, as long as, of course, the limit of g of z, which is b, is not equal to 0, right? As long as b is not equal to 0, then we can use this. So if we're given complicated functions, and if we can identify them as either the sum of a pair of functions whose limits are known, or a product or a ratio, then we can take care of, we can take advantage of these theorems to calculate the limit of the more complicated function. So we had earlier talked about the notion of a complex infinity, right? And sort of one way to think about it is that complex infinity is a number that's far, 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 far away, okay, from the origin, and its angle is undefined, right? So we don't know what the angle is, right? Now, sometimes we get into situations where we need to take the limit as a complex number approaches infinity, right? So the question is, how do we deal with that, right? Because we don't know what the angle is, right? So it turns out that there are some theorems that come to our rescue, right? Which sort of make the somewhat messy problems into slightly less messy ones, right? Now, quite bluntly stated, okay, we don't know what the angle for zero is, but a lot of the time, okay, the zero is much easier to work with than infinity. So let's see how that works, right? So let's take an example, right? So suppose f of z is, say, 2z plus 3 divided by 2z minus j, right? Now, if I'm interested in the limit of this, okay, as z tends to infinity, then this can be transformed into a new problem where we say limit of w tends to 0, where w is, 1 over z, right? So f of 1 over w, which means it's 2 over w plus 3 divided by 2 over w minus j, right? So if I multiply top and bottom by w, I get 2 plus 3w divided by 2 minus jw, and this is much easier to deal with. So as z goes to 0, okay, then basic, sorry, as w goes to 0, then the limit, okay, so this is limit as w goes to 0, limit as w goes to 0, and as that happens, the limit is just 2 over 2, which is just 1. Okay? So when you are faced with the need to take the limit of a complex function as z goes to infinity, then you can use this trick to transform it into something a little bit nicer. Similarly, we can transform some other problems where the limit itself is infinity. So for example, what I'm stating here are two theorems, right? So it's you see the equivalent sign in the middle, right? This means that what's on the left is identical to what's on the right. That's what it means, okay? So suppose you have the limit as z goes to z naught of f of z, okay? And suppose this happens to be infinity, then this problem is identical to this other problem where you have the limit of z going to z naught of 1 over f of z, okay, being 0. So if you're asked to prove this is true, then you can just prove this is true and say, yeah, because of this theorem, okay, this is true. Get it? Okay. In like line, you can pay attention to the second line, okay, limit as z tends to, suppose you have limit as z tends to infinity of a function f of z, okay, and if that happens to be infinity, then this problem is a double mess, right? It's kind of a combination of this mess and this mess, is essentially the same as the limit going of z going to 0, okay, of 1 over f of 1 over z, right, and showing that this is equal to 0. So by applying these theorems, okay, we can sometimes transform messy problems into less messy ones, right? The next important concept in calculus is the notion of continuity, right? It's intuitively the idea of smoothness, right? So if I have a function, say f of x equals x, right? Then I can just sketch that, and we know that this is a smooth function, right? A point here and a point right adjacent to it are going to behave the same way, right? I don't have a sudden jump, like it's not like you going along like this and a point suddenly jumps like that and then goes back, right? Such a thing doesn't happen. So that's the notion of continuity from an intuitive standpoint, okay? So how do we deal with the continuity of a complex function, f of z, right? Or let's first take a look at one of its components, right? So if u of z is u of xy plus j v of xy, right? Let's take a look at what it means for this guy to be continuous, right? So we're talking about continuity at a certain point, okay? We're talking about a point x naught, y naught, okay, in the complex plane. And let's ask, what does it mean for it to be continuous, right? What it means is that there are no jumps, there are no surprises. And it turns out there are three simple conditions that need to be satisfied. The first condition is that the limit, okay, as z goes to z naught, okay, so this is like z naught, okay, and the limit as z goes to z naught should exist, okay. That's condition number one. The second condition is that, this function exists at the point x naught, y naught. In other words, there isn't some surprise there, right? So basically u of x naught, y naught, okay, exists. And the third condition is that these two guys are the same. In other words, the limit of f of z as z goes to z naught is in fact equal to u of x naught, y naught. Okay, so there are no surprises at that point x naught, y naught. There isn't some sudden jump or something like that, right? Now, not all signals and systems are continuous. Okay, sometimes we'll run into some discontinuous ones, and we'll talk more about them, during the semester. For example, the unit step function is not continuous, right? So as it gets to the point 0, right, so if we look at the function u of t, right, at the point t, it suddenly jumps from the value 0 to the value 1, right? It's not continuous, right, at 0. But it's continuous here, and it's continuous here, okay, but not at 0. Now, there are also some nice theorems that help us deal with the continuity of a complex function, right? So if a complex function is said to be continuous at a point x naught, y naught, okay, is the same as saying that its real and imaginary parts are both continuous, right? So if you have a function f of z and you write it as u of xy plus j v times v of xy, if this guy is continuous and this guy is continuous, then this guy is continuous. And vice versa. If this guy is continuous, then this guy is continuous and this guy is continuous. Okay? That's a very, very helpful theorem that we can take advantage of. Now, it's intuitive, right? If this guy is not continuous, then obviously this guy is not going to be continuous, right? Because there's a jump in that two-dimensional space, right? Now, there are some nice results that are bestowed upon functions that are continuous, right? So suppose you have functions f of z and say g of z, and suppose you look at them at a particular point, say z naught equals x naught, y naught, right, in the complex plane. Then if this is continuous and this is continuous, then their sum is continuous, and so is their difference, so is their product, so is their ratio, unless of course the denominator is not 0, right? And so is their composition. In other words, if I take a point z and put it through, say, g and get g of z, okay, and then put it through the function f and get f of g of z, this is also continuous. Because neither of these functions intuitively are presenting any jump or some kind of jumpy surprises, right? If you look around this point z naught, right? And this also applies for the complex conjugates. Again, the intuition is quite simple, right? So if you have, say, f star of z, right, then it will be u of xy, okay, minus j v of xy, right? If this is smooth, then this will also be smooth. There won't be any surprises. That's all it is, right? There won't be any sudden jumps over there. So if you're looking at functions that are continuous, right, so we want to know their slope or their rate of change in the vicinity of that point z naught, right? And that's the idea of differentiation, right? You want to differentiate a function to know how quickly it's changing at that point, and that's valuable information, right? So the derivative of a complex function is defined much like in the real case. In fact, the equation looks essentially identical. So the limit of a function f of z at z naught is, okay, so we write it as, sorry, the derivative of a function f, which is f prime, at the point z naught is the limit as z goes from z to z naught of this ratio. So you got f of z, okay, minus f of z naught divided by z minus z naught. Okay. Now, it's important that this limit exists, right? Remember what we said about how you go from z to z naught, right? So you got z and you got z naught. How you get from here to here, okay, should not determine what number you get at the other end, right? So if regardless of the path from z to z naught, this converges to the same exact number, then we say that this point is, this function is differentiable at this point z naught, right? Now, if a function is differentiable, then it implies that it's actually continuous, right? But if a function is continuous, it doesn't mean that it's differentiable. And you might remember this classic case, okay? So suppose you have a function that looks like this. So you got x and you got y, and this is from the world of real variables, right? So if you have a function that looks like this, with a sudden kink like that, right? At the point, say, x naught, right? So the function is continuous, okay? But if you approach this way, you get this slope, the slope of this line. But if you approach this way, you get the slope of this line. The two different slopes are different, so it's not differentiable, but it's continuous, right? So differentiability implies continuity, but not the other way around, okay? So let's go on to the next slide here, okay? So suppose you consider a function that's differentiable, right? So you got f of z, okay? This is the same as, okay, u of xy plus j v of xy, right? We know that it's differentiable, okay? We're given that. So in that case, what I can do, and we're talking about the point z, okay? Z naught, which is x naught, comma, y naught, right? So if it is differentiable, then the following must be true, right? So if I take the limit, okay, as delta x tends to 0 of f of z plus delta x, okay, minus f of z, okay, divided by delta x, okay, that is z minus z naught, right? Because z minus z naught is delta x, right? So this is defined as sort of the partial derivative of f of z naught, okay, the partial derivative along the x-axis, right, along the x of f at the point z naught, okay. Now suppose we approach the same thing along the imaginary axis, then we can write limit of delta y going to 0, okay, f of, okay, z naught plus j delta y, oh, this should be a naught here, okay, minus f of z naught divided by j delta y, okay, and this is 1 over j, and it's the partial derivative of f with respect to y at the point z naught, right? So if the function is differentiable, that means that these two paths should not make any difference, right? You agree? So these two derivatives must be the same. So partial derivative z naught with respect to x should be the same as 1 over j, okay, of f at z naught. Now, This simple observation is a famous one. Okay, I think two different mathematicians, one guy in France, Augustin Louis Cauchy, and a gentleman in Germany, Georg Friedrich Bernhard Riemann. I think they arrived at the same thing. So for this reason, it's known as the Cauchy-Riemann equation. I like to call it the CR equation. Okay, now we can expand this out, and let's do that, right? So basically, this guy can be written as the partial derivative of u with respect to x, and we can represent that compactly as a subscript, okay? Just for compactness of notation, okay? This is at the point x naught, y naught, of course, okay? Plus j, okay, vx, again, it's this function v differentiated with respect to x at the point x naught, y naught. And this guy, okay, can be written as essentially 1 over j, right? So this is 1 over j, okay, of, u, y. So in other words, u differentiated with respect to y alone at the point x naught, y naught, plus j v differentiated with respect to y at the point x naught, y naught, right? So what is 1 over j, right? So 1 over j, in order to get that, you multiply the numerator and the denominator by, sort of the complex conjugate of this, remember? So it's minus j, and you got minus j, okay? So you get minus j divided by j times minus j is plus 1, right? So this is minus j. So this right-hand side is what you see on the screen, right? Okay? So this is minus j times uy, okay, plus, okay, just vy of xy, x naught, y naught. Okay, so let's write that. Now what we can do is that we can compare the corresponding quantities. So the real part should be the same as the real part. That means ux equals vy. Okay? And then the imaginary part should be the same as the imaginary part. That means vx equals minus uy. Okay? Or I can write this as uy equals minus vx. Okay? So these two equations, this and this, are sort of the operational side of the Cauchy-Riemann equation. And this is immensely useful. Right? So let's take a look at how it works out. Let's take an example. So I got an example here, which is f of z is, say, z cubed. And if you expand it out, okay, and just sweat through the algebra, you'll find that, okay, this is like x cubed minus 3xy squared, okay, plus j times 3x squared y minus y cubed. Okay, now we know that the cube of something is well behaved, right? So it's differentiable in this case. Okay, it's a very tame kind of function. Okay, so let's work through this. So ux, okay, so this is u, this is v. Okay, so ux is 3x squared, okay, minus, okay, you're going to differentiate this with respect to x, so minus 3y squared, okay, and uy is the same guy differentiated with respect to y, okay, so if I differentiate this, I get 0, then I have minus 3, okay, I have x, then I have y squared, right, so that'll be 2y, right, so this is minus 6xy, okay, then vx is, I got to differentiate this with respect to x, right, so I get 6 times x, okay, times y, and if I differentiate this with respect to x, I get nothing, it's 0. Then if I have Vy, okay, and I differentiate this with respect to y, okay, then I get 3x squared, okay, minus 3y squared. So is ux equal to Vy? Whoa, yes, this is the case. Is uy equal to minus Vx? Yes, that's the case, right? Check, check. This function is differentiable. Okay, and in this case, the derivative, okay, is simply given by essentially what you see on the lower half of your screen. Okay, so it is 3 times x squared minus y squared, okay, plus j times 2xy. Okay, and this is actually the same as 3 times z squared. Now if you notice, right, f prime of z is 3 times z squared. So this is kind of like just like real variable calculus, right? So in fact, that's an interesting derivation that we just went through. Okay, so let's look at a second example where f of z is simply the complex conjugate to z star, right? So suppose f of z is written as u of xy plus j v of xy, okay? This is the same as z star, okay? So if z is given by x plus jy, then z star is given by x minus jy, okay? So so if I take u and differentiate it with respect to x, okay, at xy, then I get just 1, right? And if I take uy at xy, in other words, if I differentiate with respect to y, this you get a 0. And then if I take v, okay, the second guy, and differentiate him with respect to x, there's no x here, so I get 0. And then if I take vy, okay, this guy, I have a y, so the derivative is minus 1. So if you ask the question, okay, is ux equal to vy? No. Okay. Is uy equal to minus vx? Right? Okay, they're both 0. So in any case, this alone basically tells us that the Cauchy-Riemann conditions are not satisfied. So this function is not differentiable. Now, the Cauchy-Riemann equation can also be looked at in polar form. And we keep coming back to the polar form because it's going to be, many times more convenient for us in working with signals and systems, right? So the theta is something we call the phase of a signal, and r is going to be the magnitude of a signal, and we're going to develop some language around it. So the Cauchy-Riemann equations can be derived exactly as we did for the Cartesian case, okay, for the polar case, right? I'm just written out the results in the red box on your left. So to summarize, okay, before we differentiate a complex function, we need to make sure that the Cauchy-Riemann conditions are satisfied. Okay, ux is vy, the same as vy, and uy is the same as minus vx, right? And this is a very compact way of sort of remembering it, right? This is script sheet material, right? Or mental material. So if these are satisfied, then the function is differentiable. And then the derivative is simply obtained by simply differentiating u and v with respect to x and y, okay? If the above conditions are satisfied, in other words, if the Cauchy-Riemann conditions are satisfied. And if the derivatives are also continuous, right, then we just differentiate with respect to the real and imaginary parts. And this is true also for the polar case, right? Cartesian or polar, it's all the same. Now, we are interested in functions that are well behaved, right? When functions are very well behaved, in other words, they're not just differentiable at one point, but they're differentiable in the vicinity of that point. So there are no surprises, around a point. So if I take a certain point, okay, z naught, okay, which is x naught, y naught, and if the differentiability is assured in a neighborhood of that point, okay, then that function is said to be analytic, right? So basically the Cauchy-Riemann conditions are satisfied over that entire neighborhood rather than just a point. That's what it really means, right? So when a function is analytic, it's much easier to work with, okay? Now sometimes some functions are analytic only over a certain region, or sometimes they can be analytic over an entire, plane or something like that, right? So quite often what we end up with is the more practical scenario where a function is analytic over a large extent of a region with a small number of exceptions. Okay, those exception points are called singular points. Okay, such analytic functions, even with these singularities thrown in, are quite well behaved and quite easy to work with compared to functions that are not. Okay, let's look at an example, right? So if f of z is, say, x squared plus y squared plus j 2xy, okay, let's look at the Cauchy-Riemann. Okay, we got these guys here. So this is u, and this is v. So ux is this differentiated with respect to x, which is 2x, and uy is this differentiated with respect to y, which is 2y, and then vx is this differentiated with respect to x, which is 2y, and then similarly vy is this differentiated with respect to y, which is 2x, right? So you want to ask the question, is ux the same as vy? Bingo, they're the same. Is uy the same as minus vx? Nope. Okay, so this function is, so this is okay, but this, okay, and this is not the case, right? So in other words, uy is not equal to minus vx, right? So this function is not differentiable in any full neighborhood of a point x naught, y naught. In fact, this function is not analytic anywhere. Let's look at another example. Okay, f of z is e to the x cosine of y, okay, plus j e to the x sine of y. Okay, you might remember this function from our earlier discussion where we had the function, okay, e to the z, right? So it's like e to the x plus jy, and when you expanded that, you get this function, right? Now this function has a derivative at all points, and it turns out to be analytic over the entire complex plane. So this is a surprisingly well-behaved function. So the most beautiful equation in the world is also very, very well-behaved, which is nice. Now, the topic of integrating complex functions is, well beyond sort of the scope of our course, primarily because we are limiting ourselves to a class of functions that are well behaved, okay? So, but we will have to do a couple of complex integrals, but only of a particular variety. So let me just focus on that, right? So suppose I have a function of the form f of t is u of t plus j v of t, okay? And t can vary in some interval, say between a and b, okay? And it can, in fact, it can also become equal to a or equal to b. It can be in, either an open or closed interval. Now, this is a case of what we call a parametric function. Let me give you an example of a function like that, right? So suppose f of t is e to the j omega t, where omega is some real number. Okay, you got our j and t. Suppose t happens to be time. Okay, in that case, f of t is given by cosine of omega t, okay, plus j sine of omega t. Okay, this is a signal we will encounter quite often, right? So what's interesting is that the u and the v are both parametrized by a single parameter, okay, in this case time. So this is a case that we will encounter often. And for this type of function, okay, as long as u and v are continuous, and of course for cosine and sine they are, right, things are quite straightforward, right? So if I want to integrate f of t, okay, over the range from a to b, and with respect to t, okay, then I simply spread it out between a and b, integral from a to b, u of t dt plus j, okay, integral from a to b, v of t dt. Okay, so this is a particularly simple case. Now, in general, if you look at the broader topic of complex integration, okay, there is a bit more to it than that. But in this course, in ECE 3337, we're not going to go there, okay? So I'm not going to, bore you with those details. Again, you want to probably take a good math course on that, okay? Now, to summarize, complex calculus happens in the 2D plane. So the fact that it's two-dimensional, okay, brings some new wrinkles into how we do calculus, right? Because as you go from one point to another, okay, you need to pay attention to the path that you take. And, limits that are independent of the path taken, okay? In other words, let me restate it. If you arrive at the same limit, regardless of the path taken, then that complex function has a limit at that point. And this leads to a function being differentiable as well, right? So when a function is differentiable, no matter what path you take, okay, the limit for f of z minus f of z naught divided by z over z naught, okay, it always exists. So now the Cauchy-Riemann condition is useful. It's certainly worth memorizing, okay? It keeps us out of trouble because, when you try to differentiate a function and you don't do what we need to do first, which is to check the Cauchy-Riemann conditions, then we keep out of trouble, right? Because if a function is not differentiable, then our answer is meaningless. So there are two such knee-jerk reactions I want you to remember. One is whenever there's a denominator, make sure it doesn't go to 0. And whenever you have to differentiate a complex function, run the Cauchy-Riemann test to make sure that it is in fact differentiable. Okay, as long as you do these two things, we should be just fine. Now, for the well-behaved complex functions that we are interested in this course, we can largely rely on our skills from real variable algebra, okay, and real variable calculus. But when you see functions with discontinuities or other situations like denominators that go to 0, infinity, and such other situations, we have to be a bit more careful. I've tried to show you some theorems that we can use. Try to keep them handy in crib sheet form, or try to remember them, okay? Now again, a caution that I'll continue to repeat is that we have not described the full subject of complex variables, okay? And if you want to learn that, you got to take a full semester of course from the math department. And again, as another reminder, math is like a team, like a sport, right? Now, what I'd like to tell you is that maybe you can make it into a team sport, right? So if you practice math every day, and if you happen to do it with friends, maybe it'll be a bit more fun to do. So try to focus on the basic concepts, try to get them right, and don't worry about memorizing recipes, right? These the fundamental principles are what matter. Okay, and keep at it, keep doing it over and over again until it becomes very much a part of your thinking. Okay, thank you.